Hi, today I'm going to be going over how to use MATLAB to simulate different objects as they approach a black hole. So we're going to start our code by setting up our variables. We have a couple key variables. So we have two global variables set because we're going to be using different functions from outside of our main script that we want to be calling on. So these are our two global variables that we're setting. One of them, G, represents gravitational constant. The other one, K constant, represents Boltzmann's constant, and that's used to solve for temperature. So first we put in our melting points in Kelvin, then we put mass in grams, and then we solve for the mass of a black hole. Our melting point is going to come in as one of our main things because the way that we simulate this is we took 3 cubes essentially of each material, and then we watch them accelerate. Because they're cubes, we don't have to worry about them losing their structure too much. Now, if they were different shapes, we would worry about that a little more, but the way they're set up now, we're not worrying about it. And so the one thing that we do worry about the most will be temperature of the objects, because if they get too hot, that's when they lose their structure, and we know that for sure. So the next thing we did was we put in the molecules of each element. That helps with temperature, and then we set our distances. We have our beginning distance, which is this number, black hole radius, and then we did um, our black hole plus our black hole radius plus our distance to get our total distance. And we set burner, which is going to come in later when we talk about uh, temperature, but it's really us simulating different kinds of velocities. So first we solve for forces, um, and we use Newton's gravitational force equation, seen here, using that global variable that we talked about earlier. His equation is mass 1 times mass 2. Then you get that, multiply it by g, and take all that and divide it by the radius. So once we did that, we made plots for each of the different materials, and then we also plotted them all on one graph. Now, the plot with all of them on one graph is much more useful, and I'll show you. So this is something we really want to be focusing on. It's because it's such a big time frame, the basic shape, when we look at them separated, all looks the same. You say, oh, they're pretty much equal. But when we can see them all lined up next to each other, it becomes much clearer that on which one is greater, which one's less, which one's in the middle. So here, we can kind of tell titanium has the biggest, but when we look here, it's very clear. Titanium has the most, composite is in the middle, and aluminum's the least. We then also displayed, um, right here was the new print to tell us the force applied on each object. Next, using our force, we rearranged F equals ma, and we're doing force divided by the mass to get our acceleration. And F equals ma is Newton's second law of motion. So after solving for each one, we ended up plotting the figures for them all, the same way we did before. And let's run that and look at it. So here's all of them together. And here's all of them. So notice that they're all the same. And that is something we expect because in our force equation, the one thing changing that we really look at is our mass. Our mass 1, radius, and g are going to be the same for all the equations. It's just mass 2. Now, F equals ma is that force that we got equals mass times acceleration. So since our forces and our masses are proportional to each other, they should all equal the same acceleration, and they do. We then just double check that using our logics, and that just double checks that aluminum equals titanium and titanium equals composite, and If titanium equals both of them, then composite and aluminum have to be equal. We then displayed the accelerations at each of their highest points, and then said all objects have same acceleration. Now, velocity, we are essentially assuming that this should all be equal, but we're just double checking. As you can see, we assume that all these three will be equal. We know everything else in those equations are going to be equal. So we assume that it should be equal. Now we get this equation. It's just a basic kinematic equation, rearranged just a bit to be velocity. It's really change in velocity equals square root of 2 times aluminum's acceleration, or if you're doing it with any other material, times distance. And that's just going to be whatever your change in position is. And then we plotted them very similar like we did before, plotted them all on one graph, and then ran another logic just to double check. And we can see, we plot them all. Yes, that is correct. Now we solve for kinetic energy of each object, and this will kind of tell us what we think will melt first. Now, we made another function for this one. We made function kinetic. Now, the kinetic energy equation is 1/2 mass times velocity squared. Now, we know they all have the same velocity, so the only thing that's changing is our mass. So let's look at that all. So we ran our function and then plotted it. Pretty much what we assumed, right? Very similar to our force graph. And with our force graph, we knew all that was changing the mass, so it should look similar. Now, this is correct, and we're going to use these numbers to solve for our melting. So, last and final section, we're looking at temperatures. Now, this is where our burner comes in. So instead of just plugging the velocity, since the velocity is so wide and so big and so huge, we made a smaller one so we can just look at it over a smaller bit of time. And we're going to assume they start at 0 for their temperature and then move up from there. So here's the function for this one. That's 2 times kinetic energy times 3 times number of molecules times K constant. So when we come back in here, we can see we resolve for kinetic energy just so we can focus on those different velocities that we want to focus on with burner. And then we plug it into our temperature equation. Now, I'll mention these test logs in a second. We have 3 test logs. And I'll just show them in a second. Now down here, this is our graph, and this is probably our biggest graph that we do on this whole thing. And that's because we plot each line of the temperature of each one. And then we're going to plot lines at each one's melting point, and then we're also going to add dots at each time when our object's temperature hits its own melting point. So we created a legend for it so we can understand it very well. Because there is a lot to look at here. So when we look at this, we can see our 3 lines, and then we can see our X's on our spots where, say, when the blue line hits its melting point, so that's when composite hits melting point, we put an X. Now these test logs are how we found out where to put our X's. Now they're not perfect, and I'll explain that in a second, but essentially what they are is we test at every point that composite's melting point is less than its own temperature. So that'll tell us when it's intact and when it's not, right? And they're not perfect because our temperature step size is fairly large. When we go back to our variable to look at velocity, we can see now we're looking at burner. Let's go to burner on our workspace over here. So when we look at burner, it starts at 100 and it'll go all the way up to 2,750, but it's only 100 spots. So it's stepping quite a bit every time. So those spots aren't going to be perfect, but they give us a very good approximation of that. But that's how we see, and What I think is very interesting about this is we're actually going to see that even though titanium has a very high melting point, it's gonna melt first. And composite, though it has less kinetic energy than uh, aluminum does, which is the main factor in, or has more kinetic energy than aluminum does, which is the main factor in what's really going to affect it, it melts last. And so this is really key to understanding why we use different materials when we do. For example, titanium is really strong, it can withstand a lot, but clearly it's heavy, it can melt fast, it's not amazing versus our composite, which it's the most expensive, so we can't use it a ton. But in all these situations, it's never been melting first, and it's always done well in comparison to the other two. So that gives us a very good idea of what to use in different situations. That's all I have for you. Thank you for watching.